Hi, everyone. I'd like to welcome you to today's webinar on air source heat pumps and their importance in the low carbon plans for municipalities. My name is Catherine Wilson, and I am the program manager of the Mayor's Megawatt Challenge, a program working with municipalities since 2003 to reduce energy use and greenhouse gas emissions in their own facilities. Since the Mayor's Megawatt Challenge is a member-driven program, we always poll our members on what they want to hear about. And air source heat pumps were by far the hottest topic and had the highest level of interest. This really shows that low carbon solutions and alternatives are top of mind for municipalities as they work to reduce greenhouse gas emissions and ultimately minimize natural gas usage in their facilities. We'd like to thank Kilmer Environmental for generously sponsoring this webinar and for sharing their technical expertise on this very important low carbon technology. Next slide shows our agenda for today. So we've broken down, can you go to the next slide? Could be a little bit of a delay, there we go. We've broken down the types of air source heat pumps by what they are used for. So these being domestic hot water, rooftop units and air handling units, and space heating. We'll also discuss how to best control the equipment. And the last 15 minutes of the webinar is reserved for questions from the audience. There's just a few housekeeping items on the next slide. So please use the Q&A option for questions related to content, and you'll see the Q&A button down at the bottom of your screen. Questions will be answered during an audience Q&A at the end of the webinar, but select questions may be answered during the webinar in the Q&A chat box if they're easy to respond to. But all questions and responses will be circulated in a question and answer document after the event, along with a recording of the webinar. So like I said, you'll see answers in that Q&A session during and at the end, and anything we can't get to, we'll certainly share. And if you can reserve the chat for any technology questions or questions that are unrelated to content, that would be great. Okay, next slide. So this webinar is going to be conversation style. It'll be moderated by Frank Camilleri from Enerlife. Frank will be leading the conversation and asking questions to the various panelists in the appropriate sections. So I'll now ask each of the panelists to introduce themselves. Ed, would you like to go first?
Yes, thank you. Ed Carney, one of the partners at Kilmer Environmental. I've been in the HVAC business for over 30 years, and it's nice to have interest in energy efficient technologies. In the past, that wasn't the case, so it's kind of an exciting time to be in HVAC.
For sure. Thanks, Ed. And again, we'd like to thank Kilmer for not only sponsoring the webinar, but also for providing your technical expertise and experience with us. That's wonderful. Craig, would you like to go next?
Sure. Hi, I'm Craig Edwards, the Manager of Energy and Utilities with the City of Vancouver Facilities Department. And yeah, we have a large portfolio of buildings at the City of Vancouver, about 600 buildings of various types, including a fairly large commercial portfolio. And the city has really aggressive targets for reducing greenhouse gas emissions and showing leadership. We've got our own building bylaw. We can set our own building code, which is aiming for zero emissions by 2030. So we're trying to show leadership in our own city-owned buildings, and we have really aggressive targets for new construction. We're building all our new buildings to a passive house standard and 100% electric, and then with our existing buildings, when we have to replace heating systems, we're trying to replace them all with low carbon solutions, take out gas-fired equipment and put in heat pump systems. So we have a lot of projects completed and underway with heat pumps and air source heat pumps in particular, because especially in Vancouver, we're a warmer part of the country than the rest, and I'm sure they're a bit easier to implement in Vancouver. And then BC is also blessed with clean electricity, so converting from gas to electricity really helps us with reduce our greenhouse gas emissions. So yeah.
Great. Okay, thanks, Craig. And we really appreciate you taking the time to share your extensive experience with this technology and bringing the municipal perspective to our groups. It's fantastic. Adrian, get to go next.
Thanks. Yeah, my name is Adrian Chiquetto. I'm the account manager here at Set Point Building Automation. We're a BAS vendor, turnkey solutions using the Reliable Controls product. I was really fortunate that Enter Life and Climate Challenge Network asked me to participate in this, and glad to just offer the point of view from the BAS side, as trying to integrate to these devices, or integrating to these devices, I should say.
Yeah. Thanks, Adrian. Yeah, controlling the equipment is key, and we certainly value what you're bringing to the table here. Okay, last but not least, Frank.
Yes, so name is Frank Camilleri. I'm the VP here at Interlife, and my background is mechanical engineering, focused on energy efficiency, and over the last close to 30 years, and probably over the last 5 years, low carbon, very much a strong focus in low carbon. So very excited about this topic, and to be here to facilitate this conversation about air source heat pumps.
Thanks, Frank. All right, well, I'm going to turn it over to you now to walk us through all of the content we have here.
Okay, great. No, thanks, Catherine, and thanks all the panelists for participating in this. So Catherine gave a little bit of a of a prelude to why we're doing this, but just to sort of set the stage on air source heat pumps and what we're going to focus in on today. We know that having participated and come up with low carbon plans, air source heat pumps are really key to reducing greenhouse gas emissions in buildings. They're one of the key tools that and pieces of equipment that we have at our leisure, and so it's going to be very important. That's why we want to talk about them in more detail. There's been this more so probably in the past probably decade or so. Conventional heat pumps generally haven't performed extremely well, and there's this perception that they're not a really good alternative, and we want to just again bring everyone up to speed based on the panelists here, who have quite a bit of experience either in providing equipment, controlling equipment, or actually using it, just so everyone becomes familiar with some of the latest trends in these. But new generation of heat pumps actually are becoming more and more suitable for colder climates, and can perform well temperatures below 0 degrees Fahrenheit. And they're getting better and better with their efficiency, and although not able to quite eliminate supplemental heat for every application, but they're getting better at low temperatures and reducing the need for supplemental heat. So that's a bit of the background and sort of setting the stage for this webinar here. Okay, let's get right into it. So this is basically a slide just describing a bit how heat pumps work in general. And basically, it's extracting heat. So the top part there is all the different sources you can extract heat from when you're looking at the heating side of things, and then putting it into the bottom side, the heat sink, and that will depend on what you're trying to use it for. As Catherine mentioned, we'll be focusing, according to the agenda, we'll be focusing on 3 key areas, which we'll get into it. But today the focus will be on the air side. So on the top here, it'll be on the air side piece of things here. So we'll focus on extracting heat from the air and putting it into either an airstream or a water stream. That'll be the main focus of today. So again, it just uses the refrigeration cycle, kind of like cooling does, but just reverses the things it's extracting heat from the outdoors. So without further ado, let's focus on the, again, just reiterating the areas we will focus on as it was in the agenda. We're going to be, we've noticed these are kind of the 3 trends of where air source heat pumps are mainly used for. Domestic hot water use, for rooftop units, air handling units, and for space heating, boiler heating kind of requirements, right? So, and we'll tackle each one of them because the reason why we decided to break it up into these categories, we think there are some unique challenges to each one of them and unique trends going on each one of them. So we felt this would be the best way of actually going through them. So we'll start off with the air source heat pumps for domestic hot water needs. So just a little bit of background on domestic hot water source, air source heat pumps. So we're seeing, having worked with many municipalities, small and large, we've seen a couple of key different types that are being used, or at least the applications are. There's smaller type applications that are generally self-contained, with no ducting, basically just cooling the surrounding area. Again, this is mostly for lower demand or residential type applications. So again, some of the smaller municipalities, this could be very much applicable for. Again, some of the smaller systems can also have evaporator ducted to the area requiring cooling, or to the outdoors, depending on the specific needs. Ideally, it would be great if you can actually make use of the cooling that comes out of this, right? So again, IT rooms and things like that. Commercial systems are typically, they're larger. They can be located outdoors with heat tracing on water pipes, but they can also be located in mechanical rooms. And we'll hear more from the panelists about the different types and the different experiences that they have. And they are fairly relatively straightforward to retrofit in commercial type buildings. These applications are not very foreign. They have been used and becoming more and more common, let's say, right? Okay, so let me just get to the next. Oops, going too fast here. Again, just continuing on the domestic hot water needs, the key characteristics. The self-contained ones, the ones that are usually not ducted outdoors, that usually use the space around it. Basically, there are no really issues in terms of operating temperature range. Again, we'll focus on the operating temperature ranges of each of these different types of equipment, both for domestic hot water needs. Again, because the focus is going to be emphasizing how these pieces of equipment do in cold climate. Again, the self-contained ones really don't need that. Don't have much of a concern, but for the majority of ones in larger buildings, it's typically ducted to the outdoors or to areas where cooling is needed. We know that Craig has good examples where he's actually been trying to duct it to an area where there's IT closet nearby where there's a requirement for cooling. So it's great taking advantage of the cooling that comes as a byproduct of this and using it somewhere useful within the facility. And the good thing about it is that many of the existing technology can operate and provide 130 degrees Fahrenheit, even in fairly cold climates, even in minus 30 degrees Fahrenheit with one pass, without using a secondary heat exchanger. So I think that domestic hot water, from an air source heat pump perspective, domestic hot water is probably one of the more advanced types of air source heat pumps and needs. But anyways, that's what we're observing. So I guess a question for you, Ed. What is the most common type of installation are you seeing from your perspective?
Well, I guess when you look at the heat output from any of these heat pumps, you need some pretty good, tonnage to accomplish the kind of heat that you need for domestic hot water. It's a pretty big load, or it can be. And the small ones that you put right in the mechanical room are great if, like you say, you have the space and you have the heat gain in a mechanical room. But I would think for most applications, you have to be careful with that because they can quickly overcool the mechanical room. So what we're seeing mostly is larger systems that are, outdoors. The whole, it looks like a condenser located outside, and the domestic water is directly piped out, and you have to heat trace it. That's typically what we're seeing. I'll also say that it's one of the easiest applications, as you said. I'll confirm that because with one heat pump, you can literally go. Because of the cold incoming water, we're able to take that refrigeration system and raise the temperature all the way up to usable temperatures around 130.
No, that's great. Thanks for clarifying that. Yeah, that makes sense. Again, as larger applications, you really have to be mindful of where the cooling is going, and you can run into issues obviously in mechanical rooms where you're somewhat limited. Just continuing on that, the operating ranges, which I just mentioned over here, that they can operate even in minus 30 degrees Fahrenheit. What are you seeing out there in terms of technology? Even though it can go down to minus 30, are you seeing the air source domestic hot water heat pumps being packaged with backup heat And if so, what types are you usually seeing as that backup?
So with the nature of the refrigerant-based air source heat pumps, what happens, anybody's system, is the colder the temperature outside, the performance slowly drops off. So you do get to a point when it's really cold outside that, yes, we can still operate our units at -30, but the heat output may not be enough at that temperature. So yes, we have built-in electric backup heaters that will automatically top up and work in conjunction with the compressor to give you the heat you need. There's an optimal amount of sizing that you do here. If you want somebody that really wants to do this all with heat pumps, well, yeah, you can spend a lot of money and put a lot of refrigeration equipment in to do it, even at those low extremes. But as we'll talk about in future slides here, it comes a point where it just becomes very expensive to put in a lot of these systems when you can have just a small amount of backup electric to trim on those hours that don't occur that frequently.
Mm-hmm. Thanks, Ed. That's a very good point that we'll talk about, as you mentioned, in future slides, about the practical aspects of this and how do you size these things for for proper economics and so forth. Where's that balance of heat for air source heat pump versus backup and the type of backup, right? So glad. Thanks for sharing that. And it sounds like electric backup seems to be the most common type with domestic hot water air source heat pumps. Then that's good. Okay, great. Great, thanks. So just moving along here, kind enough to get just a bit of a visual on the non-ducted one. So here's just an example again to demonstrate how one of these things might look like. So this is kind of an example of a non-ducted one, as we talked about too, because it's in the ambient air, if you will, if it's in the mechanical room, for instance. So you can see the performance of this non-ducted air source heat pump for domestic hot water. It improves the COP, the red line there, improves as the ambient is warmer, mainly because of the lift, the amount of heat that you have to get out of it. It's available, it's there, right? So, but you can see it's pretty flat. Again, this is when we're not really concerned with the ambient, the extremes that you get with the ambient ones that the ducted ones need to, or the ones that are actually located outside that need to deal with that. So again, just a little bit of information for that on this one here. Talking a little bit about the different types that are out in the marketplace. There are refrigerant-based air source heat pumps, and I guess this, and their CO2 based ones as well. And question for you, Ed, on this one over here is maybe you can expand a little bit on what kind of refrigerants you're seeing more of, serving domestic hot water needs.
Yeah, refrigerant is a pretty hot topic right now because the changes are coming to the types of refrigerant that are used in these machines. So R410, which we're currently, it's pretty readily used in most common commercial and residential refrigerant systems, is getting replaced by 454B. That will be a hard cutoff date in the United States within a couple of years. It's a little bit longer here in Canada, but a lot of the manufacturers are in the States, so that will be affecting us. And another common one that we're using now is R134A, which is getting replaced with R513. And of course, CO2, which we'll talk about.
Mm-hmm, mm-hmm. Thanks for that. Yes, I mean, with the focus on climate emissions and emissions reductions, the topic of global warming potential associated with the refrigerants that are used in here becomes a hot topic, as Ed mentioned as well. So those refrigerants typically have considerably higher global warming potential than CO2. So we always have to be mindful of that, and I think that's where the second sort of type that has come out and it seems to be evolving right now. So the CO2 based ones, I mean, the good thing about it is the global warming potential is 1, so extremely lower than most refrigerants that are available out there. So that's one of the advantages of that. and they tend to be more efficient as well. So that's the other good thing about these emerging CO2 based air source heat pumps. The other one of the disadvantages, unfortunately, is that at least right now the cost is quite a bit more expensive than your standard refrigerant based air source heat pumps. Approximately twice the cost of those. So a question a bit more for you, Ed. What trends are you seeing in the uptake for CO2 based air source heat pumps for domestic hot water?
Well, as you mentioned, the global warming potential of the refrigerants is what's driving the changes. And I believe they're going to get even more aggressive as time goes on. So, these new refrigerants, yeah, they're much lower than the old ones, but, they want to drive that down to next to nothing. And CO2 has a lot of promise, being GWP of 1. And what's neat about it is for domestic water, it's very highly effective, again, because of the low entering water temperature coming into the system. These things, the system we have is capable of -20 all the way to 190 water temperature. Not that you need to take your domestic to 190, but it's capable to do that in one shot. So you're also getting much higher COPs, up to 6, whereas you're up to 4 with a standard domestic water heat pump, air source heat pump. So yes, the initial outlay is higher, but the cost modeling is pretty exciting about CO2.
Good. No, thanks. That's great. I guess as we continue to address the climate change, technology is trying to catch up and trying to adapt, and yeah, it looks like CO2 is going to be one of those key areas of focus, and you're starting to see it now, it sounds like, right? So which is great. I know a lot of people, we keep hearing in the marketplace, obviously we're post-COVID, I'll say that softly, but we know that wreaked havoc on distribution, logistics, and things of that nature. What are you currently seeing as the lead times for these types of air source heat pumps?
Well, they're still in around 30 weeks or less. They've been able to hold that currently, at least with the water side units. The air side are actually under 20 currently. It's all over the map. Some manufacturers are still 30, 40 weeks.
Oh, wow. Okay.
Sure, our audience is aware of that.
Yeah.
But we've been fortunate that we're under 30 with the water side and under 20 with the air side.
Okay, that's good. That's good. And it sounds like that we're hoping that this is more of a temporary thing. We're trying to bring that down to more reasonable lead times. I guess typically we've seen, again, equipment lead times around the 10 to 12 weeks. So I'm sure you guys are striving towards that, or at least you're who you represent are striving towards that, which is great. The electrical service implications, of these, most of these have been generally, using natural gas as the fuel source for it. And just what's your observation in terms of the implications on the electrical side for these units?
Yeah, well, if you are replacing gas, obviously you're changing fuels over to electric, and having electric backup as well as your compressor, the two things are definitely going to be a higher electrical disconnect than you had with your gas heating appliance. So that's something to keep in mind. But unless you're, depending on the type of facility, you should have sufficient power, and usually it's just a local. What I mean by local is local in the area that you're using it may need the power upgraded to that, but it generally doesn't affect the feed into the building or anything that dramatic.
Okay,
at least with domestic water.
Domestic water, yes, yeah. That's a hot topic, and thanks for touching upon that. Is that distinguishing the requirements of a local need. So obviously the local infrastructure that disconnects the wiring going to these domestic hot water pieces of equipment, it's going to be higher because it was natural gas fired, very low electrical requirements. So you're going to need that, but However, typically, given the sizing of domestic hot water needs relative to the infrastructure and the main feed coming to the building, typically you're not seeing this as being using these as sort of being that trigger where you have to upgrade your main electrical service to not here. The other items we'll talk about afterwards, I think, tend to lead to that, but this is, I guess, one safe area where you're noticing too that it doesn't usually run or drive you or force you to run into a major electrical infrastructure upgrade to the building. So great, thanks. Question for you, Craig. We understand that you've have experience with both types of these, both refrigerant types and CO2 based in your facilities. Is that right?
Yeah. So yeah, we've used integrated heat pumps, refrigerant based heat pumps, and CO2 based heat pumps in our facilities. In general, we're building a lot of new buildings, and as I said, our standard is 100% electric. So our starting point is if the loads are really small for domestic hot water, we'll just put in an electric resistance tank. And then if it's kind of a medium type load with a fire hall or an operations workyard or something like that, then we'll typically put in integrated heat pumps, the ones you're talking about with the heat pump on the top of the storage tank. They already have built-in backup in each of those tanks, and we'll put a couple of those in, say, a mechanical room at a fire hall, and then duct the cold air into an adjacent communications room, or we'll design the building so that the transformer rooms and communications rooms can get cooled by those units. And then in larger buildings with a larger domestic hot water load, we've been designing them with larger heat pump systems, 410A and 134A systems we've used on a few projects, and then also CO2. We'll talk about the CO2 example at an outdoor pool, but we've got a couple of other projects under design right now, a new community center where we're putting in a CO2 based heat pump, and we're retrofitting a large housing project with a CO2 based heat pump. So we've got experience with all of them. I would kind of disagree with your comment about the larger systems being fairly easy in terms of controls. They're not. You need to design it with a lot of storage. You need to design it so that the heat pumps don't cycle, that they start up and run continuously, and because if they cycle, then you're going to kill the life on them. And so the controls for the larger systems are actually quite complicated, I would say. And
oh, okay. No, that's a good perspective that you bring on. You're living and breathing with these things. You're living with the operational side of this equipment. So that's an interesting comment that you're making. So great for the audience to be aware of that, to be very mindful of that. And so storage tanks end up being a part of the equation, is what you're saying, to help deal with trying to make the loads more constant. So you're minimizing the cycling that could, like you said, could damage the compressors, I guess, over time if it's excessive. Is that? Okay,
yeah,
good.
definitely.
Okay, good. And I know we're going to get into a bit of your example soon, but just any quick comments for the audience about any things that sort of notable about either CO2 or refrigerant that just that you need to be mindful of, or?
Yeah, well, we've the reason why we've tried out our first CO2 heat pump was because the technology became available. It didn't really used to be available until a few years ago, and the product that we used at our Kitsilano outdoor pool just recently became available, so we used that. But the main driver was because the refrigerant is low in global warming potential, and we put in a ton of heat pumps with 410A and 134A, and our experience is that we do get leaks in those refrigeration systems. We're trying to reduce our greenhouse gas emissions from our buildings, and we're being quite successful by using heat pump systems, but we do end up with refrigerant leaks, and then if you've got a high global warming refrigerant that leaks out, then it kind of negates the progress that you're making in trying to reduce your emissions. So we're, really focused on trying to push the industry towards lower global warming potential refrigerants. And as Ed says, they're coming, but they're still not really here yet. And so at least for now, we can start using some of these CO2 heat pumps and take advantage of the low global warming potential. The other reason we like those systems is because they're high pressure, so they need a different type of compressor. They've used reciprocating compressors, which are kind of like a car engine, and they're really durable. So we don't have direct experience, but they're built to last, 25 years instead of these smaller heat pump systems with scroll compressors, and where we're finding we're already getting failures in those in less than 15 years. So we're enthusiastic about CO2 from a durability perspective as well.
Mhm, mhm. No, that's great. Thanks, Craig. Yeah. Two key highlights. Again, the drive towards lower emissions, both on the refrigerants. Interesting to hear your comment about noticing leaks. You're right. You sort of negate what you're trying to accomplish if you're dealing with many of those. And then an interesting comment about what I know you haven't had, and we'll talk about your example shortly. But I know that you haven't had your CO2 machines in for too long, but the general impression that you're getting is that you're probably will be hopefully have longer life out of some of the compressors just because of the design of them, right? So that's great. No, thanks. So just moving along, I think one of the I'd like to just share some examples of some analysis that's been done on this. So there is a community center example that we've done analysis on in Ontario, replacing domestic hot water, typical gas-fired with air source heat pumps. The specific facility had two smaller type residential domestic hot water units and a larger one. And we did the sort of the economics associated with replacing it with air source heat pumps. Again, you could see here below here that the low carbon solution initial cost are quite significantly higher, and we hope that over time that'll come down. But even with the current pricing that we have, that initial cost is a lot higher than the sort of the business as usual case, which is sort of gas for gas. But the total cost of ownership is an interesting one. Is particularly a little bit less than what you're seeing on the with the business as usual. So that comes often as a surprise. A lot of the impressions out there are that low carbon generally is a lot more expensive, and yeah, it is more expensive from an initial cost perspective, but over the life of the equipment, generally we're finding that it actually is the same or even better than the business as usual. I know really the point here is really what's the best low carbon solution, because it's really not an option, but I think it's an interesting point here, and a bit of an interpretation of this is that again, the initial cost here was $220,000 for the above type of scope of work, where this one here is about close to a tenth of it. But when you look at the operating costs, and what's really driving this is the carbon tax. When you start taking into consideration the carbon tax, and you take advantage of the COPs that Ed was talking about, that Craig's talking about, when you factor those items into it all, you really get some pretty good annual savings, especially with the aggressive increase of carbon tax over the next little while. So again, it was just an interesting one we wanted to highlight, and on this specific application, it saved approximately 32 tons of CO2 annually. The other thing I wanted to talk about was, here's just again another example. Wanted to look at a different province which has slightly different utility rates, a little bit lower on the electrical side, tends to make the economics look a little good. So that was just an Ontario example. This one here, again, similar to the other case, initial costs are quite a bit higher. But however, in this case here, because the electrical costs are lower in the province of Manitoba, that the overall costs of it. So the interpretation of this is you have a net present value for the low carbon case at $196,000, but the net present value of the business as usual, and that really is the initial cost plus all the operating costs along the way. You get a gap. A gap of at least $44,000. You're $44,000 ahead just without any funding that's available. We're finding that, at least in this particular example, this was taking into consideration, which many of you are aware of, the green and inclusive community building funding that was available at the time, which unfortunately just closed at the end of February. But again, the good thing that's very promising about this is that low carbon solutions can actually have a good a reasonable financial return over the life of the equipment without funding as well, right? And we know there's still other funding programs available out there. Good. So just moving along, this is actually the example, Craig, that we wanted you to talk a little bit more. This is the CO2 one. So maybe you can just give a little bit of background on this one here, and sort of some of the driving factors and things you want to highlight for municipalities that are on the call.
Yeah, sure. So so this is our Kitsilano outdoor pool, and we installed a CO2 based domestic hot water heat pump system there last year, and it started up at the beginning of last summer, so it's ran last summer and it's running again this summer. The instigation for the project was that we had a gas-fired boiler that was at the end of its life and needed to be replaced, and our capital maintenance department was going to replace it, so we came along and said, okay, let's try out a heat pump system here instead. It was a 600 MBH gas-fired boiler. So we installed the product that's shown here. It's the first installation of this brand of CO2 heat pump in BC. I don't know if in Canada, Aegis Link heat pump made by Watts. It's a European product. I believe it's made in France, and then it's built put together in Texas with the control package and everything. And it was the first installation in BC, so the distributor brought it in, and that's the picture on the left is shown in the shop. He brought it in the shop for different people to come by and have a look at it. So yeah, we installed it, and it's been quite successful. We've designed it with it's got 3 200-gallon storage tanks that's served by the heat pump. We duct the cold air out. It's in the mechanical room for the pool room with the boilers, and we duct the cold air out through a stack. And yeah, and the key with CO2 heat pumps is that they need a really cold return temperature. So they work really well for domestic hot water heating because you've got the domestic cold water coming in. But it's really important that you design it so that the storage tanks and all the controls are built so that you have a really cold return temperature coming to the heat pump all the time, and that the heat pump doesn't cycle. You want to start it up and let it run kind of all day. So you design it so you have a reverse cascading system where the heat pump sends the hot water in reverse flow through the 3 tanks in reverse to how the cold water comes into the system and goes through the system. And then we put in a controls package. We hooked it up to our building automation system, our DDC system, so that it's completely controlled so that it turns on when the storage tanks get fairly cool, and then it gets charged up. The storage tanks gets charged up like a battery, and then we turn off the heat pump when it's charged up enough that we start getting too warm a return water temperature going back to the heat pump. This project was quite successful because we've learned from some other projects where we've had similar installations with package controls that haven't worked out very well, and we've had to rip them out and put in full DDC controls to get them to work properly. So, but we took the lessons learned from other projects and applied it to this project, and it's worked out really well.
No, that's great, Craig. Thanks for the background. And yeah, a common theme that we're hearing from you is that you really got to be mindful of the trying to avoid the cycling. So it's good that you've taken that or tried to take that into consideration in the design. The reverse flow piping that you referred to is a good way of dealing with that. So I guess a note to the audience really is to be mindful of that as well. And you get to know about the the efficiency in the operation of CO2 in particular. Really likes to see that cold colder water to operate effectively. So some great tidbits of information here. And just Craig, just for everyone's sake, how long has this been in place now for? How long has it been in use?
So it started up we finished the installation in May last year. So it ran in last summer, and then the pool was closed for the winter, and now it's running again this summer. So it's a bit more than a year, but not a full year. But
Yeah. Okay. No, that's good. That's good.
Yeah, and we haven't really had any issues with it. No maintenance issues or anything.
Oh, good. Okay, that's great to hear. Yeah, that's fantastic. Okay, great. So moving along to sort of the next area of topic. So again, we talked about domestic hot water needs. Now we want to focus on air source heat pumps for rooftop units and air handling units. So again, similar to what we talked about at the domestic hot water ones, want to talk about the different configurations that are, prevalent in the marketplace. So we're seeing rooftop units with individual air source heat pumps, one per rooftop unit. Then you have another configuration where the rooftop units and air handling units can have a central air source heat pump using hydronic piping. And then we're also seeing a bit of, and I know Craig has experience with this as well as others, rooftop units with variable refrigerant flow connecting to all rooftop units. So we'll talk a little bit about each of them beforehand in some of the slides that follow. And again, the operating temperature ranges will depend on a specific piece of equipment. But I'd just like to pause for a second here and ask Ed, based on your observations as an equipment provider, what are the different configurations that you're seeing the most of these days, and from the above there?
Yeah, probably the easiest thing to implement is just a like-for-like replacement of a rooftop that's equipped with the air source heat pump functionality. So any of these units you see the picture of here could be ordered as an air source heat pump. And so, you've got a certain power coming into the unit, and you can use that same power to make your unit into an air source heat pump. It's fairly quick and easy, and very modest premium to do that. So that's the thing we're seeing the most of. Mm-hmm. If you want to totally decarbonize, then you got to look at something a little bit more with more power, whether it's a central system where you have a new hydronic piping running around, or VRFs where you have two pieces of equipment now. You have a separate VRF unit and the air handling side. So options 2 and 3 can definitely get you more output, but it's definitely going to be higher cost and more time, because it's got to be designed and all that. Whereas just a like-for-like replacement of a rooftop is pretty straightforward. Mm-hmm.
Okay, no, that's great. Thanks. Yeah, we always want to be aware of what's out there, but also some of the practical aspects, and we'll talk about that a little bit later as well, for sure. Great. So just want to talk about some sort of the performance specifications of this. So just using rooftop unit where typically, a certain amount of air, not 100% makeup, but a certain amount of air. You can see, again, no surprises here, as we've talked about, that the capacity of the heat pump based on outside air temperatures, obviously decreases quite significantly, especially if you get into the 2 degrees Fahrenheit range. So again, something to be mindful of. But again, the rooftop units probably in this range are typical, maybe closer to the 20 or 30%, depending on what you're seeing. Maybe 4% is a little bit on the high side, but you could see almost a 40% range, if you will, 40% of the peak capacity of it. So again, something to be mindful of when you're looking at these, and each equipment manufacturer will have a slightly different curve. I wanted to highlight fresh air makeup unit, again, which is exasperated in this case over here because of the fact that you're dealing with 100% fresh air. You have the advantage in the previous example where you're mixing it. right? So in this case here, you don't. But what I wanted to highlight over here is, it can't really handle much. At least this specific example can't handle too much at these extremely low temperatures. But there are ways to deal with it, and that's where the next sort of slide comes to play, and that is the use of heat recovery wheels, especially when you're dealing with a makeup air unit. This can considerably improve your performance of your air source heat pump. So again, here just examples of winter and summer conditions. It just significantly improves your entering temperatures into your air source heat pump. So we advise, especially if you have 100% makeup air unit, that you definitely consider including these, and we'll show you sort of the performance curves of this. You can see here that now that same unit that we showed before, where it had some quite a bit of difficulty in the lower temperatures, anything below sort of the freezing mark, you saw some issues with. But now the combining the heat capacity with the heat pump capacity with the heat wheel capacity, the heat wheel actually performs a lot better with the colder temperatures, because now it's actually got a higher delta T. So anyways, this is what we're seeing more and more in observing in the marketplace, especially when it comes to makeup air, that you definitely include a heat wheel, and you could see with that heat wheel, COP does improve. So every BTU is becoming more and more important in this new world of low carbon. So a lot of attention being paid to heat recovery, and this is just no different than that perfect example of this. Next, just want to talk a little bit about another example of sort of performance curve, sort of heat demand versus air source heat pump capacity. This is just an example of an administrative building in the Toronto area. And we have over here, a bunch of different curves, and this is, touching upon, Ed's comment about, how do you size these things? It's very strategic how you deal with it. In each building, you have to think a little bit about it. Depending on the climate, again, in Toronto, relatively cold climate. So you see here, the red line over here is a certain brand of air source heat pump. It's that has this curve in terms of its heat capacity, and then but you can see that it drops off quite a bit when it hits the below the freezing mark, around the 30-degree mark. But then we have a whole bunch of other curves. You'll see the blue, the green, and the darker blue, and the yellow, and the gray. Those are just varying sizes of VRF systems. So just wanted to plot and just show you, the characteristics of the different types of air source heat pumps that are available. This is actual data. So the blue, all the dots there represent a data point of actual real data. It's a requirement. It's a gas requirement for this building. So this is where we're dealing with real data, and you can see here that depending on what you choose, you can get into, you can see how much of the gas you would actually offset, right? So again, depending on which size of it, if you get to the bigger ones, the one at the top there on the VRF side, we found that you can get to close to 100% mitigation of gas. However, as Ed pointed out before, it's really a costing exercising. What is the right fit for your specific facility? The amount of heat pump capacity versus heat pump capacity and your backup source, right? So again, just wanted to present that. Different specifications or different operating parameters for different types of systems. Just wanted to highlight too that VRF generally has a flatter curve, and generally that's because of what we understand is that slightly quite a bit big oversized compressors, and they'll vary the flow to handle the varying loads, right? So just wanted to move on to some of the practical aspects that you've talked about already. So I think one of the key things that you've already touched upon is what's happening in the marketplace is really trying to leverage the existing electrical infrastructure. Or in domestic hot water, we talked about it, that usually that doesn't, not in all cases, but usually doesn't require an electrical infrastructure upgrade at the main building. Locally it does, but this one here, it's very easy with gas-fired rooftop units to have a requirement of quite a bit. It could be a big increase depending on how much how much of the heating you want to be recovered by the air source heat pump and the backup electrical heat. So what we've observed, and it would be great for Ed to comment too, is just really leveraging the existing electrical infrastructure, resizing the heating component of the air source heat pump to match the unit cooling tonnage, right? It's sort of that practical side of things, and this definitely requires a hybrid solution. And there is a bit of a premium of that. And then again, using backup heat to eliminate gas usage. Again, just highlighting the fact that, especially in cold climates, this typically has some pretty big, can have some pretty big implications on electrical infrastructure. So, but comment for you, Ed, you touched upon it beforehand on the, but maybe you can elaborate a little bit about what you're actually really seeing in the marketplace for the hybrid solution and some of these, there's some of the options that come with it. What are you noticing out there?
Well, when a client wants to replace their rooftop unit with an air source heat pump and you are doing a like for like, first thing you got to realize is that rooftop unit has been sized for the cooling load, not the heating load, at least on the refrigeration side. And the refrigeration, your compressor is your biggest power draw, assuming that you have a gas-fired rooftop unit. So you're limited now to how much heat you're going to get out of that power supply. There's a certain wire size that's feeding that unit, and it's been sized to handle the cooling. So the heating compressor needs to be bigger if you want to service the entire load, heating load in the winter. So you're kind of limited then by the wire size that's coming to that unit in terms of how big your air source heat pump can be. So the compromise is, the lowest cost is just a straight replacement, and work with the wire size that you have. You might get lucky. Motor efficiencies have gone up. So in some cases, we can go to slightly bigger tonnages without changing the wire size. So you might get lucky that way. But what you're basically doing is taking advantage of the majority of the hours of the year that occur. So if you ever look at ASHRAE bin data for any city, you'll see that most of the hours of heating occur in the 40 to 60 range or in around there. That's where the curve really swells, and that's where you're going to have most of your operating hours. Mm-hmm. As a matter of fact, if you were to take 0 degrees Fahrenheit as your sort of cutoff for the typical heat pump in Toronto, the hours of the year less than 0 degrees Fahrenheit are about less than 1%. And if you move up to Sudbury, about 4% of the year occur below 0 degrees. So, you sort of keep that in perspective when you're looking at this. If you want to completely get off of gas altogether, then you probably will need a bigger electrical feed just to handle the very low extreme temperatures.
Mm-hmm. Yeah, thanks for that, Ed. Yeah, we're always looking for practical solutions. We know in some cases some buildings have a feeder capacity limitations. Feeding the building, the grid nearby is sometimes strained already, and this might be your only option. And in cases where it is available, it can be costly. So this is something that like I said, that's great to hear that people are actually using. And to your point, when you look at the gas consumption that results in this type of a solution, given it will obviously depend on what climate you're in, but a lot of the hours of operation with weather in terms of bin hours tends to be in that range where the air source heat pump would be sufficient, and when you're sizing it this way, so you're not really losing too much. You could probably get, again, depending on the climatic area that you're in, it could be 60, 70, 80% of gas reduction with this hybrid solution. So anyways, definitely an option for consideration when replacing rooftop units, right? So it's just great. So just continuing on here, again, every BTU counts. You heard me say that. You're hearing that from the panelists. One thing to keep in mind too is the, especially we're dealing with the rooftop units, the double wall, the cabinet construction is important. Being mindful of that cabinet construction, whether it's insulated or not, or insulated well, can mean a big difference. When, in cabinets where they're not well insulated, you can lose a handful of degrees due to the ambient. So again, we strongly suggest that that you look into that when it becomes part of your evaluation criteria, especially in extremely cold climates. This becomes a bigger factor. Again, every BTU counts in this new world of low carbon emission reduction, right? So. So as we did with the domestic hot water, I wanted to talk a little bit about some of the financial analysis associated with air source heat pumps, rooftop units versus business as usual. So we had an example of a community center in Manitoba, replacement of 3 smaller, gas-fired rooftop units, kind of in between the 5 and 10 ton range, with air source heat pumps complete with electric backup. And again, in this case over here, the initial costs are actually similar because we're avoiding the gas. So this specific example didn't have a requirement for, or felt that we could get away with the electric backup, given the building is actually a nice rig, so it has quite a bit of capacity. But again, each specific situation is different. In this case over here, you'll notice that the initial costs with rooftop unit, like a business as usual versus versus air source heat pump without backups and not the hybrid solution, they're pretty close in cost. You'll see that the cost savings difference, initial cost is only it's less than $1,000. But you can see that the total cost of ownership, it really shines in this example over here. Again, just trying to highlight the fact that, when you take into consideration carbon tax, which is a reality here in Canada, it can significantly push you towards using low carbon solutions. It's not there's been this perception out there that low carbon generally is a big financial burden, and it really isn't the case when you look at the overall total cost of ownership of each different type of equipment. Now, again, in this case over here, this was not a hybrid solution. This was just an electric backup, if you will. It was a hybrid, but it wasn't relying on gas. If you did want to have the gas as a backup as opposed to the electric, because in some buildings, again, you are constrained in terms of capacity, that there would be a smaller premium, but still the overall sort of total cost of ownership, being in this case here without even any funding, any grants out there, being as high as $235,000, you could easily support the premium associated with a hybrid solution. So again, just the messaging here is that you need to do the math on it, but it can be fairly attractive financially to proceed with the low carbon solution versus the business as usual. Here's another example, again, looking to you, Craig, as sort of leading the charge out in your neck of the woods. Maybe you can describe a little bit more about this example and a little bit about the replacement and how it's been working for you.
Yeah, sure. So this project, we call it the Kaslo Hub. It's a commercial building owned by the city that we rent out. The project was going through it had a new client with a new lease and going through a major interior renovation. So we decided to replace the HVAC system at the same time. Had 15 gas-fired rooftop units on the roof that were poorly zoned and poorly controlled. There was ductwork that had been cut off with different renovations over time. So we decided just to put in a new central system. So we put in a new system, hydronic system with 4 pipe fan coils serving all the spaces, and then 2 AirMech air to water heat pumps producing both hot water and chilled water. So these are 4 pipe air source heat pumps with a chilled water buffer tank and a hot water buffer tank. So there's always hot water available and chilled water available. This is a typical solution that we apply on new construction as well. This is probably one of our most common solutions when we build a new building, new large building. We look at either geo-exchange or air source heat pumps, and if geo-exchange is not viable for any reason, then we end up with this solution very commonly. This project was built about 4 or 5 years ago. It was one of our first large air source heat pump projects, and it works quite well. The 4-pipe fan coil system works really well. It was a real challenge to commission. We learned a lot along the way. With lessons learned, we're applying for other projects.
Mhm. Okay, no, that's great. That's great that this one here was successful, and it sounds like from the descriptions, you're learning at each one of these, and you apply it to your future projects, which is good. Especially again as you try different variations of these of air source heat pumps and how you're using them. Just curious in terms of approvals process. Obviously, again, no different than showing you some of the examples of the financial analysis. Initial costs are obviously typically higher than just a typical, one-for-one replacement. In terms of creating the business case for, upper management for approvals, are you looking at total cost of ownership? Is that what they typically look for in giving you sort of the go-ahead for something like this? Is that what you end up having to use, or?
Yeah, so any retrofit project, we do a feasibility study and do an economic analysis. But we have such aggressive targets for reducing greenhouse gas emissions that we have an internal carbon pricing policy that we developed about 5 years ago.
Mhm.
And we've set internally a price on carbon. It started out in 2018 at $150 a ton, and it raises by I think it's 6% per year. So now it's up to about $170 or $175 a ton. And we do that, you include that in the economic analysis. So, it helps tremendously with the business case. So unless the project really doesn't make a lot of sense because of extraordinary costs, most projects make sense from an economic perspective, easily make sense if you add an internal carbon price to it. But that process is almost redundant anyways, because our standards say that we're going to build all new buildings all electric anyways, so we don't really even have to do the analysis. And when we retrofit equipment, our policy is also to replace gas-fired equipment with low carbon equipment. So that's our starting point. And unless the project really doesn't make sense, so the policy is we will replace it with a low carbon alternative unless shown that it's not viable.
Mm-hmm, mm-hmm. Oh no, that's great. That's helpful. Yeah, I mean, it does help, as you mentioned, when you have a citywide policy that going to gas, replacing with gas is really not an option to be considered. It's now you're looking at the alternatives if you're going to go totally away from that. So that's great. I know some of the other municipalities, across the country that maybe even on this call might not have that luxury, but I guess, but that's good. And again, just want to highlight the previous examples that I highlighted were based on just federal carbon tax implications. I know that in BC they are more aggressive than the federal ones, but it can make sense even financially. Certain types, most of them can make sense financially when you just follow the carbon tax associated with the federal government alone, right? So thanks for that piece of it, that explanation, Craig. Here's another example. I know this is a newer construction. I believe, and this one over here again is maybe you could just spend a couple of minutes really quickly on this one here. This one I believe is still not completed. It's under construction now. Craig, maybe you just can explain this one here a bit more.
Yeah, well, so here's an example of a project where we're replacing rooftop units with a VRF system. So so this is our Carrisdale Community Center. It's got a pool, regular community center facilities like a gym and meeting rooms. It's also got a senior center associated with it. We're actually doing a major mechanical upgrade on the project with a grant from the Green and Inclusive Communities program that you were mentioning,
Okay.
where we're putting a heat recovery chiller in the pool and converting the whole system, the systems in the entire building to lower temperature systems and using the heat recovery from the pool, and as well as adding an air source heat pump to top up the energy needs for the building. But the reason I put this here as an example is because the left-hand side of the picture here shows the older part of the community center that has 10 rooftop units that are at the end of their life and need to be replaced. And we've had consultants look at it in terms of what's the most practical for converting them to heat pumps. And the recommendation we've gotten on this project and a number of other projects is to just put in new rooftop units with electric backup, and then put in a VRF system. VRF is variable refrigerant flow. So in this case, 2 condensers, and then the refrigerant would be piped to each new rooftop unit with refrigerant coils in the units for both heating and cooling. So that's the solution that we're applying here. And we've been applying that to a number of other projects as well, instead of replacing the rooftop units like for like. And the VRF units, they generally work better down to lower temperatures, and we can control them with our DDC control system instead of having packaged controls on each rooftop unit. And so, it's a way that we like to go.
No, great, thanks. Yeah, this is a great example, different than from the previous example where you converted to more of a fan coil, 4-pipe fan coil system, but this is where you actually did replace with rooftop units, not quite like for like, because you change the system, you're totally off of gas, but good to see a different example, and we know that it's good to see that you got experience with the different configurations, right? VRF being one of them, and we know that just standard air source heat pumps, also very applicable. So again, there's a variety of things to be taken into consideration when you're evaluating different options for replacement of rooftop units. So again, thanks for that. The one I want to move into is the next one, sort of the last of the 3 topics, really is the air source heat pumps for space heating needs. This is the one that probably presents the especially in colder climates, the biggest challenge on the electrical infrastructure. Again, air to water source, air source heat pumps is the common thing we're starting to see more of. And again, it can be used for rooftop units. It's touched upon in the previous topic, but also for perimeter and fan coil hydronic systems. Again, this one here, if you're in existing buildings, you don't have the luxury of redesigning your terminal units, especially in colder climates. You need the higher temperatures, right? So how do you deal with that? And we just want to touch a little bit upon that in this section of the webinar. So moving on to here. So again, Ed touched upon it, and we have Craig over here who experiences slightly milder weather than in the central Canada. But here again, just to highlight the bin hours, the amount of hours that different climatic regions within Canada operate. So you can see here, Vancouver, big peak around the 50-degree mark, which is great. So tons of hours there. Again, a very different, very unique profile to some milder weather. But again, that exists in Canada. And in Toronto, you see it's flatter. But I think one of the things to really highlight is that a good part of the hours, even in a slightly colder, in a colder climate like Toronto, you got a good part of the hours that are above freezing, right? So again, you really need to be more sensitive to the cold temperatures and how you select your equipment. And again, each climatic region has its own issues. But I wanted to highlight, again, that just two examples of, different climatic regions within Canada and kind of the number of hours operating in each of the areas. Here's just an example of 3 different heat pump operating ranges and what they're good at. So you can see here the piece of equipment on the right-hand side, which is, on the left-hand side of this, we see leaving water temperatures. So that type of application, you can see provides, 180-degree water, right up until when it gets cold outside, you get into, obviously it starts to decrease a little bit, but it's probably good till about, 15 degrees Fahrenheit. So that would be, maybe a selection that you would consider in a slightly milder climatic region. And then you've got a couple of other examples here. There's sort of the green, the top left corner there, that heat pump, air source heat pump has that characteristic again, the high temperature. So when you're restricted, because the terminal devices in an existing building, you're sort of, that's a big constraint for you. You're still going to want to see the high temperatures. Again, that unit there, just operates a little bit better with colder temperatures outdoors. So that might be something that's more suitable for, a colder climate than the other one on the right. And then we have the other example there where it actually operates really well at very cold ambient temperatures. The problem bit with that, unfortunately, is that, in that case there, at least that one there, the temperatures are closer to the 145. So again, you need to look at your application. You need to look at the constraints that you're faced with. If you got a new building, definitely, as Craig suggested, is you build your terminal devices, everything around, really good operating range that makes sense for the equipment that's available today. Many municipalities that we know that are constrained with in existing buildings with the terminal devices, so they have to rely on higher temperatures. But it's good to know that there is current technology out there that you can get this higher temperature. So again, just wanted to highlight that piece of it a bit. This is overlaying the two, which is just a bit of an extension of what I was saying, is that when you overlay these two, you would want to use a different operating range type heat pump for something a little bit more milder, like Vancouver versus Toronto. You might go with a slightly different one here. So I guess a question for you, Ed, as an equipment supplier, what are the main differences in the design? We see 3 different types of equipment, 3 different operating characteristics. Maybe you can help explain for the audience here, what are the differences in the equipment design for each of them that you might want, just so they understand it a little bit more.
Yeah, I think the main takeaway with this slide is just to show you, it's maybe a little more technical than we need, but it's just to show that each compressor has its own, each compressor manufacturer and model has its own window that it operates in. And not one compressor can do it all, right? So Transom has done a good job of just kind of mapping that out and putting it into a different model to figure out, what is your application? Is it domestic water heating? Is it, super high temperature water heating or mid temperature water heating? And from that, we can fit the right unit into the application.
Mm-hmm. Okay, no, that's great. Great, thanks. Yeah, that's great. Again, to emphasize the fact that there's, different air source heat pumps for different applications, and the good thing about it is that you do have some choice out there. It's not that there is only one type and you're constrained with it. It looks like the marketplace is adapting and trying to take into account, the different applications and the different constraints with each one of them. The high temperature being one of them, the low ambient temperature being another one, and trying to find the one that best suits your application is important. Just kind of moving on to the next slide, which talks a little bit about the high temperatures, because I guess there's this perception out there. I know from my perspective, this was always a bit of a constraint that I've seen, but I understand that the technology's gotten better. I mean, to get the high temperature loops that most of the facilities, existing facilities are constrained with, particularly in cold climates. We're seeing that there's technology out there. You need a bit of a cascading design, if you will. You need a couple of sets of heat pumps to do this. So you would have, I guess, air source heat pumps on the primary loop, and then on the interior side, you would have water to water heat pumps to do it. But I guess the important thing to highlight here is that if people think that using air source heat pumps is part of the solution to get 180-degree Celsius is not doable. I mean, that's not the case. We know that the technology can be a little expensive, but it is there. I mean, you can do it again a little bit more expensive to do this route here, but again, just want to make it known that the technology is available. You have to do it kind of in a cascading way, a couple of stages here, where you have a primary loop that brings it up to a certain temperature, then you need the other set of heat pumps to boost it up a little bit higher, right? So that's good. I'm not sure, Ed, if you had any comments you wanted to highlight or add to what I was saying.
Well, just quickly on that, your two types of heat pump there. This topic is on air source heat pumps, the bottom 3 units, which sit outside and obviously take heat from the outdoor ambient. But because they, in this application, they can only get to a certain temperature. That's why you would put in water to water units in series with these things, and they can now take it up to a temperature, much higher temperature. So if you've got an old building that has old rads that need 180 degrees, you might have thought, hey, I can't do that with air source heat pumps. Well, you can, and you still can be above a COP of 1 with this arrangement on the extreme days. So it's still a win over the boiler.
Okay, so thanks for adding that to the conversation. Again, in most cases, when we're talking about space heating needs, we know that again, if you're replacing gas fires, particularly in low climates, you are looking at fairly big implications on the electrical infrastructure. So again, just keep that in mind. I guess of all the 3 different topics we talked about, this one has probably the most impact and implications on it. But you're always looking for, as Ed mentioned, always looking for what's the best way of dealing with from an operational perspective. You highlighted the fact that the COP generally is better than 1. Which beats electric backup, and then again the times that there's quite a few hours that you're operating this equipment where the COP is a lot better than 1, and so you're getting the benefit of that from an operational perspective and less constraint on the grid too as well. So again, a lot of these factors in there. Just want to highlight the fact that it's doable. You can use air source heat pumps, can be part of the equation for existing buildings and meeting space heating needs, again, to highlight this probably will impact your infrastructure. However, again, there is a solution out there in the marketplace, and things are going to get better and better as technology improves, as the performance of this equipment improves in colder climates, right? So I just wanted to move to the next one. Again, another example, Craig, from your perspective. Maybe you can describe a little bit about this one over here. Some of the key drivers of this and the performance of this from your expectations perspective. Yeah.
Sure. So this is a retrofit project we did at the Bloedel Conservatory, which is a large greenhouse dome open to the public in Queen Elizabeth Park in Vancouver. It's full of tropical plants and birds. It's got a huge heating load and a huge cooling load. It was already had a large chiller and cooling tower that needed to be replaced. It was an R22 based chiller at the end of its life, and R22 is being phased out, so it was going to be replaced anyways. So we took the opportunity to replace it with an air source heat pump instead, to provide both heating and cooling to the building. So this is the picture of the air source heat pump that we use, an AirMech 210-ton unit. It's a 2-pipe system that switches over in the summer to cooling and in the winter to heating. And the unique strategy we applied here is that the building has 8 air handling units in it with the heating coils and cooling coils. And in our buildings in Vancouver anyways, the cooling coils are always much larger than the heating coils. So they've got more capacity. So what we did in this case was we ran this air source heat pump through the chilled water coils for the building, and we left the heating coils alone hooked up to the backup boiler. So in the summer, it provides chilled water for cooling the building through the cooling coils, and in the winter it provides heating through the cooling coils. And then if the heat pump can't keep up for some reason, then still got the backup boiler there for providing the backup heating. So the main challenge that we ran into with this project is we've only got one air source heat pump. So it goes into defrost, and so the biggest challenge for us in Vancouver is temperatures close to 0 degrees Celsius, slightly above when it's pouring rain, and slightly above 0. Then we get a lot of frost buildup on the coils because the coils are cold in the rain. So it's not even the colder temperatures that are the biggest challenge. So it's actually the temperatures just right around 0. So in this case, we have to, the unit goes into defrost, and that's been a little bit of a challenge with this project. We were actually expecting that half the unit could go into defrost while the other half would keep going heating the building, but it turns out that we didn't order it that way, so the whole unit goes into defrost. So what we've done is just increase the loop temperature to try and to keep it being able to heat the building while it's in defrost. But anyways, it's been a very successful project. We installed it over a year ago. We've got a year's worth of data, and we've reduced greenhouse gas emissions by about 90%. I think you've got a slide. The next slide.
Yeah, the next slide over here talks about the reduction.
And here's the gas consumption for the building, and like I say, it's dropped by about 90%. We still use the gas boiler with the heating coils for helping it heat a little bit in extreme weather in the winter. But this is just a brilliant strategy, and we've applied this strategy in a few other buildings. We've got a police building where we've done the same thing. We put in an air source heat pump, send the heating and cooling water to the cooling coils, and then leave the heating side alone. And in that case with the police building, so that provides most of the heating through the cooling coils, and then the building has a perimeter radiation system as well that's high temperature, which isn't served by the heat pump, and we put an electric boiler just to serve those high temperature heat loads in the winter, and that's a really successful project. But we've been applying this strategy and replacing chillers with heat pumps that provide heating and cooling, and it's working really well.
Yeah, that's great that you're able to try to leverage the existing equipment, cooling coils being of a good size and trying to take advantage of that, which is great. Again, just so that's great. I wanted to talk a little bit about, in the interest of time here, this is I guess another one that you had the luxury of a newer building, a new development, maybe in a quick 30 seconds.
Sorry to interrupt, Frank. I was wondering if maybe the next two examples we could maybe just cover in the Q&A document, maybe just provide a little more information, just because I want to make sure that we cover controlling the equipment. And as I mentioned in the chat, looks like the Q&A, we won't have time to cover that live, but we'll certainly answer all of the questions. We've got 15 great questions in the Q&A that we will definitely circulate after the webinar.
Sure. Yeah, exactly. So thanks for that. Yeah, thanks for that. So the next two examples were more from, a greenfield where you're having a full redevelopment. And again, if you have that luxury, just really briefly, if you have a luxury of designing something from you take advantage of the lower temperatures where these air source heat pumps really operate well. Again, lots of equipment selection out there, both made locally. We understand there's some good manufacturers here locally as well. Don't have to get all of this abroad. So just again, there's a lot of selection out there. Just wanted to get to, as this last topic is as important, is controlling the equipment. Wanted to get sort of Adrian, who's been there on the panel observing and not really talking much, but just his take on this. I know that the air source heat pumps have built-in controllers and integrating to the existing BS. Maybe Adrian, you can talk a little bit about your experience with air source heat pumps and integrating to them?
Yeah, sure. So I mean, in general, the majority, or if not every single one of these devices are now coming with a factory controller in there. They're complicated machines. They're complicated machines with refrigeration cycles. They need to be controlled by the people who manufacture them because they know how to control the inner workings of that machine best. With that being said, I mean, I think it's very important, and Craig touched on this, multiple times. I think the biggest takeaway here is, integrating to a piece of equipment is not really a hard thing anymore. Connecting BACnet IP, BACnet MSTP, that's the easy part. The hard part these days is kind of, using the various, forms of documentation that the manufacturers provide to really understand kind of what the heat pump does, how it does it, what logic it takes on its own. Because at the end of the day, it's not really our job specifically to control the inner workings of the piece of equipment. We're really setting the stage for the equipment to, operate at its optimal point. And I think that's a really important thing to remember. And like I said, Craig touched on that a few different times, where if you don't have, all the support systems and all the parameters of everything else that's going into this working properly, you're really not going to get the gains, and you're really not going to get the efficiency. And you might have some, equipment longevity problems later on due to short cycling and things like that. So I think that's a very important key piece to remember when you're thinking about these things.
No, that's very helpful. Again, good point that, integration is not a problem, integrating it with all the protocols that are available, but it's making sure that, I guess, all parties, manufacturers, BS service providers, and the engineering consultants / owner are all aware of the capabilities of it and what you can and can't do. This technology being newer than, traditional boilers and traditional just cooling equipment, I guess it's got a bit of catching up to do, perhaps, in getting everyone aligned to optimizing these systems here. Again, just in the interest of time, I know, Craig, just you mentioned already, the defrost cycle as being one of the issues that you've had to deal with. Any just quick last minute comment you want to make on this frontier on the control side that you think people should be aware of?
Yeah, well, I completely agree with Adrian that, the equipment itself, you want to have it run on its own, but the real challenge is understanding what the load is on the building and how you want to integrate the equipment into the load so that it runs efficiently and doesn't cycle too often. And, you can't treat this equipment the same as a boiler. And the biggest challenge is that the consulting engineers often don't know exactly what they can do. They develop a sequence of operations, and then you get this piece of equipment that doesn't necessarily do exactly what the sequence of operations is specified for, and then the controls contractor has to figure it out. And everybody has to accept that that's kind of the reality with most of these projects, and it's a bit of an iterative process. The engineer has designed the sequence. Everybody needs to try and figure out what the equipment can do in the design stage and spend more time on that, and then work with the controls contractor. And what we're finding is that it is an iterative process that we have to go through. We have to have really top-notch commissioning agents to help us get the equipment working right. And then we find, we have to come back afterwards and see how the equipment's operating and how it's integrated with the building. And we have to rewrite a lot of the programs and the sequences, following up on these projects a year later when we find out that, the heat pumps are cycling too much and we're having other types of control issues. So, it's not a slam dunk. It's definitely a challenge that everybody has to accept and embrace.
No, that's great. I mean, like I said, just a quick highlight here. I know we're near the end of the webinar here. But yeah, again, just on the control side, be mindful that it is more complicated than traditional equipment, and people are still learning about what it can do and can't do. And there seems like to be, quite a few different factors that you need to take into consideration when you're operating and designing this equipment. So, so again, thanks for that.
And sorry, Frank, just one last point, just to echo also what Craig was saying. If you can if you can bring in all the parties early on, if you can bring in your BAS vendor, you have a BAS vendor that you trust, you can bring them in early on in the design phase and in a lot of the conversations that go into these on the conceptual side. It's a huge benefit further on down the road.
Yeah, that's a great recommendation, Adrian, and I think it sort of piggybacks on what Craig's saying is, doing a proper job at the design stage and getting all parties involved. That makes a lot of sense to me. So thank you to all the panelists. I guess Catherine, I guess you want to put some closing remarks on this at all. I know we didn't have time for questions. I know that we plan to answer them all.
Yeah, if you just want to advance through the slides there, I think
yeah, sure, go ahead.
the next one was the defrost. We did cover that,
which we talked about. Yeah, exactly.
Yep. As I mentioned, we have 16 questions in the Q&A, and we will be circulating a Q&A document not directly after the webinar, because we'll need to respond to them, but we'll send out a recording of this webinar with responses to all of your great questions. And if you think of something after the webinar, please feel free to reach out and I'll add it to the list and we'll get that documented there. We have a member session coming up July 26th. So members, please stay tuned for details. And my contact information is here. So again, please reach out if you have any questions, ideas, thoughts, anything you want to add here. And yes, so thank you again to all of our panelists. It was really excellent information that you shared with everyone. And again, thank you to Kilmer Environmental for sponsoring and for providing your technical expertise, and Craig and Adrian for your expertise as well. Thanks so much, everyone. Hope you enjoyed the webinar and take care, and we'll talk to you soon.
Great. Thanks.
Thank you.
Everyone.
Thank you.
Bye now.